Good morning everybody and welcome to this tutorial titled Simulation-Based Testing with BeamNG.Tech. In this tutorial we'll see the basics of how we can use this simulation for testing self-driving car software. My name is Alessio Gambi. I work at the University of Passau and today I will be your speaker. But this tutorial is a joint work with me and other people, including Pascal Maul and Mark Müller from BeamNG. They will be around today for addressing technical questions on the simulator and how it can be used to achieve effective testing. So simulation-based testing with BeamNG.Tech. But what's BeamNG.Tech? BeamNG.Tech is a photorealistic, accurate, soft-body physics engine that is capable of real-time simulation of vehicle dynamics and damages on all consumer-grade hardware. To give you an idea that how it looks like a simulation in BeamNG.Tech, if you see here, the software is simulating the parts of the car, which also lets you create realistic crashes. So to give you an understanding of why we are using BeamNG.Tech as a simulator for generating tests and simulation-based tests for self-driving cars, let's look around who's using it. So, so far, there are a number of papers published in major software engineering and software testing conferences, including ESEC-FC and ISTA, and several tools that rely on this simulator for search-based testing. To name some, we have Asphalt, DeepJanus, and AC3R. And lately, we have a new another paper called Deep Hyperion, which again uses the simulator to generate tests. In addition to that, this year at the tool competition, here the SPST workshop, several people submitted their different tools that are based on BeamNG.Tech, and maybe, who knows, after today you will use it as well. So let's move back to the tutorial, starting with the goals. So this is a beginner tutorial. So we are going to cover the basics of the framework and how they can be used to generate simulation-based tests. And we also will exemplify some examples of automated test generator. Let's start with the first part, getting started. So the resources of this tutorial are published online at this GitHub repository. So you are going to find their setup instruction, the code examples that I'm going to run here, copy of these slides, and links to additional resources. So you still have the chance to walk through this video again and then run the commands that I'm running here, and and then look at examples and then work with them. To install the simulator, you don't have to do much more than downloading it, which is a big tarball, and extract it. At that point, assuming that you have space to run it, you can run it. So one note here is that officially this simulator can run only on Windows, but you can also try it on Mac using Parallels. For example, the videos that you're going to show today in this presentation are recorded using a MacBook Pro that runs BeamNG inside a virtual machine handled by Parallels. So to run the simulator, there are different ways. The simplest way is to double-click on the exec, and that is located under the bin folder in the BeamNG distribution. Could be a nice and initial thing to do, so you can browse existing maps or create new content. So for example, here what I'm going to do is, this is running in my virtual machine inside my Mac. I start the simulator. The simulator it takes some time, it goes up, and then you can browse it. Content, For example, you have a list of scenarios, or you can use the free roam activity to look at the levels and the maps. Another way for running a simulator, which is what we are gonna do in the remainder of this tutorial, is to use it and start it using a Python API called BeamNG.Py. So BeamNG.Py is an open source project that is available on GitHub, maintained by Mark and Pascal, and it can be also installed as a library from PyPy. So to run the simulation, you need one call. So you instantiate the object, you import it from the package BeamNG.Py, you need the class BeamNG.Py, and you define it to be running on your localhost. You provide the port, because this acts as a server to which your Python client is gonna send commands. We specify home and user, BeamNG home and BeamNG user, as you see. For simplicity, I store basically everything under C, so I know there are no spaces and what's not. And for the remainder of the program of this tutorial, we will use exactly this configuration. So once you instantiate this object, BeamNG.Py, you have to call open. When you open with the parameter launch equal true, that's the moment where the library spawns a simulator and attached to it. When the job is done, you can close it by calling it BeamNG.Close. So this is the basic example. So if you see here, there is a pattern. You open, you do things, and you close. That's why the BeamNG.Py also comes as a Python context manager. So if you are not familiar with Python context managers, those are classes that you use by means of the with keyword in Python that ensures that when you call them, they are gonna initialize and release automatically when the flow of the control flow exit the block. And this is how we get things running. So we assume that we downloaded the simulator, we installed the dependency with Python, and then we can run it. Now, in the second part, here I introduce basically the main elements that, in my opinion, in our opinion, form a test. So the pieces that you need to run a test, and then we are gonna see in the last part how to put all together to generate tests automatically. This is our reference architecture for simulation-based testing. We have a test generator on top. This can be a human writing a test or an algorithm that generates tests automatically, that generates some tests. Tests are passed to a Testcontroller. The Testcontroller is the component that needs to start, set up, and tear down tests. So you can think of Testcontroller like frameworks like PyTest or UniTest, and we are going to use mostly UniTest here. But a Testcontroller can be any form of a Python script that can interact through the BeamNG API with the underlying simulator. So this controller is the one that does the job. In this case, we assume that BeamNG.Tech, the simulator, is a black box. So we don't see it, and we refer to it by means of the API that exposes its functionality. So the API hides the underlying simulator. The other two components that are relevant in this architecture are the runtime monitors. So the runtime monitor is this component that collects data from the running simulation, and is the one in charge of basically checking oracles. If something happens, then this component will notify the test controller about a passing or a failing of a test, and then the test controller will stop the test and move on. On the other side, there's a driving agent. Driving agents are basically the test subjects. So they are started or connected through the test controller, and they observe and control the simulation. What does it mean? That they have a way to read the data at runtime from the running simulation, compute the control command that drives the car, and send them back to the simulator to have those cars basically driving around. And those are the components that we are gonna see in a moment. So this is the agenda for this part, is the anatomy of a simulation-based test. There might be different ways of doing that, so don't take this for granted. So we start with a precondition to have a running simulator, then we see how to set up the environment and the initial condition of the test, mainly how to place obstacle, how to configure and set up the oracles and the test subject. And finally, we are going to look at how we can add some dynamism to our test. Let's start with the precondition. So when it comes to running the simulation, we assume that the simulator is running. Now, there are two main possibilities. Either we restart the simulator, a fresh instance of the simulator for each test, or we try to reuse it. Starting the fresh instance in general prevents or reduces the effects of pollution between states, and in a sense also reduce the flakiness of tests, but it takes more time to execute tests because every time you have to restart the simulation and wait that the simulation load and such. Reusing the simulator instead allows you to save some time, which may be a selling factor when you have to run many tests. In general, in this tutorial, we're gonna see how we use one instance at the simulator at a time, but nothing prevents you, provided that your hardware is capable enough to run multiple concurrent instances, so you can even parallelize the simulations. But we are not gonna see it here today. So to start a fresh instance, this is a unit test class. What you have to do is that in each test you can open and close a new simulation. Okay, here I'm using the Python context manager. So I defined two unit tests, and in the first I open the simulation. This is gonna start the simulator and close it, and then I repeat the second time and then repeat the same for each test. Instead having a shared instance, so reusing the simulator across tests, you need a slightly different method. So what you can do is to have a class method that are executed only once for each test, but not for each test method, where you set up the simulator and start it. Now we can call this like the main client of the API. Is the client that invokes the open command with launch equal true. So this will cause the simulator to start and to be stopped after all the unit tests are executed. Now in our test, we are gonna still need to use and access this instance of the simulator. What we can do is to again instantiate this BeamNG class, but instead of calling open launch equal true, we call open launch equal false and deploy false. And why we do so? Because in doing so, the library knows that it needs to connect to a server listening in localhost port 64256 without the need to spawning another process. So this is basically connecting to a running simulation. Now at this point, in order to disconnect, we need to close the socket connection, but not the simulator itself. If we call client.close, client A or client B.close, now we will gonna kill the entire simulator, failing to basically share it across tests. But it's still, what I want you to know is that it's possible. And we are gonna see how we are gonna use this exact setup when we need to, in our example of automated test generators. So assuming that a simulation is running, now we have to set up our tests. So one way of doing it is to start from the environment. So BeamNG.Tech execute tests as driving scenarios. Driving scenarios takes place in the context of levels. Levels are kind of logical containers or deployment unit, if you want, that contains a terrain, a map, all the props, arts, models, materials, all the data that you may use in the simulator. Scenarios can and we will be defined programmatically. Okay, so we can take existing maps, and there are 19 at the moment, very well defined. There more can be downloaded, and you can also create your own manually. And then on top of those maps, on top of those levels with maps and all elements that can be used inside the simulation, we are going to create tests. So to give you an overview on how they look like, this is basically the levels that you can have. So the existing levels are very well defined, are manually crafted, and then they are rich in the details. Each of these level comes with a name. And then what you have to do is, after you start BeamNG, you create a scenario. So there is a class scenario in which you give the name of the level that you want to use, and the name of the scenario that you want to use. If the scenario is an existing one, it will be loaded. Otherwise, it will be created for you. At that point, you can make the scenario, meaning that the API is gonna create all the necessary files on your system to program the simulator. You load it, and then you start it. One central point is the ability to procedurally generate content. And this is a unique feature of BeamNG.Tech, which makes it really powerful, but one of the best choice when it comes to search-based software testing, because it gives the tester the full control of all the elements of the simulations that can be programmed directly in, for example, Python. In this case, we focus on roads. So roads are defined as a sequence of nodes, and nodes are points in three-dimensional space on extended with a width of the road. So a road is a sequence of points. At each point in space, you tell the system how wide is the road, and the system is going to create a road for you. There are other attributes that you can set, including the ID, the material, the lane configuration, and the direction of the road. For example, here in this code snippet, I create a straight road, and I give it a name to a new scenario, test scenario. I define a new road that it's made of this road rubber sticky. We will see later what's this. This is the name of a material that exists in the simulator. I extend the nodes with the road, and then I make the scenario. So the scenario is gonna look like more or less like this. So this code is available on GitHub under load scenario and roads.py, and the code that visualizes road is under the module visualization.py. So as you can see here, the road is made of 4 nodes. Each node defines the same width, and because the nodes form a straight line, we are going to obtain a straight segment in the simulator. So one last point is about lane markings. So we generate roads in terms of their geometry, but and then we attach to them, we define what material makes them. So materials does not necessarily comes with lane marking. So we know that for testing that computer vision or vision-based driving agents rely on the features of the road. You know, the red, the yellow central line, or the solid white line on the side, or what's not. We need to generate lane markings at themselves in the simulator. Otherwise, if the texture that is associated to the material we use to generate the road does not contain those features, they will just be plain. So one way of doing that, and this is what tools like Asphalt and AC3R do, is to imagine roads as made of layers. The base layer is the concrete. So we can use a material like this road rubber sticky, which is basically asphalt, a concrete layer with no lane marking. What we can do then is to draw on top of this the lines themselves. And how we do that, we reuse this logic of creating roads, but we change the material. The alternative, which is adopted by tools like Deep Janus, Deep Hyperion, and the tool competition pipeline for this SBST tool competition, is that we can create a texture that indeed embeds the lane marking, and then let the simulator adapt it or to the road geometry. And once you have done this, the generation of the road is exactly the same, like the basic one, but it will render slightly different. Okay, for example, this is how it will render. Now, this is how you can set up the environment. the environment, the roads, and lane markings. Let's move on and see how we can set the initial conditions of our test. This is mainly about placing vehicles and objects or obstacles. So BeamNG.Tech allows multiple vehicles and objects to be placed at arbitrary location and rotated in any direction. And those vehicles have a model. Okay, models are listed under the vehicles folder in the distribution. You can see Autobello, you can see, I don't know, Caravan, and many other things. ATK 800, which is the default one that we use. The counterpart are obstacles or objects that are static. Things like buildings, concrete barriers, and they can be either modeled in outside programs and imported into the simulator, therefore used also in your test, or they can be procedurally generated. So to place vehicles, you need to instantiate the vehicle class, provide a name that is unique in your simulation, and a model. So the model, like ATK hundreds, Autobello, or City Bus, in this case is exactly the model that you see in these folders under the vehicle folder, and added to the scenario with the add vehicle call. So, and this basically will import in the scenario whatever model you want. This is for placing vehicles. For placing objects, we follow a very similar approach. So the objects, they have collision maps. So if a car crashes into them, as we will see in a moment, they actually damage the car, but the object itself, it's simpler. Okay, so you can place it wherever you want, and they will stay there. The choice that you have as tester when it comes to placing objects is either generating them from scratch procedurally. That's one possibility. The other possibility, which comes handy when you want to work with complex objects, I don't know, a concrete barrier with a specific visual pattern, red and white stripes or something like that, right? Those objects can be imported. What you need is one of these DAE file. This DAE file, I'm not going into the detail, is basically a 3D modeling file. What you do and what I've done, for example, in this case, is to browse the different levels that exist already in the system, and they come with tons of those models. Choose the one that I liked. So, for example, this concrete road barrier, and then tell my simulation, look, this is what you have to take. Create a static object, use this shapefile, and import it. So that's how I can set up the initial condition. Okay, I place the static objects and the vehicles. Now it's a moment for moving away from the conditions and looking at the oracles. So when it comes to testing continuous controllers, which is different from regular unit testing and testing of regular application, we need to think in terms of positive and negative oracles. So positive oracles are the ones that establish when the test pass. Negative oracles, that are the standard one, decide when it fails. And why it matters? Because the test subject is a continuous controller. We cannot wait the end of the test to decide that the test passed. So this is the usual X unit pattern. If the test complete without triggering any assertion, then the test pass. But here there is no end because it's a continuous controller. So we need to make sure that we can identify also when the test pass. Classical example of positive oracles are target areas. So the car must drive from the initial position to some target area, and if it reaches the target area, the test passes. Conversely, examples of negative oracles are timeouts. Okay, the car did not succeed within some time. The fact that there are crashes and damages to the car, lack of movement, and even unsafe or forbidden areas. Oracles works on data. Okay, they can be defined on object states, position or rotation. The car should stay in its own lane. absolute values like simulation time, physical quantities, maximum speed or acceleration, and even other sensors. These data that are required to evaluate the oracles can be obtained by modeling the simulation using the sensor abstraction. So BeamNG.Tech provides you this abstraction of sensors of different types, state, timer, cameras, electric sensor, LiDAR, sonar, ultrasonic, just name one, that you attach to the car. And when the sensor is attached to the car, then it can be read. And this is what these runtime monitors indeed use. For example, here I have the simplest example, the sensor state. Okay, so sensors are defined under the module BeamNG.Sensor, and we import state. Okay, so we have a state sensor, we attach it to the ego vehicle, and then once you start the simulation, after we load the scenario, we can pull the sensors. We pull the sensor, we get the data, and then after that we can read it. Once we have a sensor, then we can define an oracle. For example, we can define a target area oracle, something that it's based on position. In this case, what I've implemented is a simple oracle in which we provide a location and a radius and a state sensor. And this oracle will check whether or not the position of the car is within or not this area. When it comes also to collect data, we may need to collect a large amount of data that then it must be processed on the critical path. Okay? Imagine that you have everything running inside the main loop, then you get images, point cloud from LiDAR and what's not that you have to analyze. And this may take time and introduce performance overhead, then impact the quality of the simulation, because the simulation is running, you are overloading your machine, and then you may introduce some sort of lags between the observation when you collect them and the reaction or the monitoring of your oracles. To reduce this impact, BeamNG.Tech comes with this idea of having synchronous simulations, and then synchronous simulations are basically simulations that execute in steps. You define the steps, which are the granularity of your simulation. For example, 60 steps for each second, corresponding roughly to 60 frames per second. You can have more or less, and then you can tell the simulator, now you progress the simulation for this amount of steps, and then you stop. And once the output of your monitoring of control is ready, then you can resume the simulation for another loop. So to have synchronous simulations, you have to set the steps per second, define the simulation as being deterministic, and then you pause it. And then what you can do, what we usually do is in a main loop, we make the simulation progress, calling the BeamNG.Step, providing a number of steps. If we provide 30 steps, after we define that in each second we have 60 steps, this will correspond of progressing a simulation for half a second. This let you control the frequency of monitoring and frequency of control. And then once you have done this, you can do your work and then resume the simulation. So now we know how to, read data using sensor and define oracles. What about test subjects? So we need to connect to the ego car, instruct about the test goal and what's not. So the ego car is our test subject. Actually, the logic that controls the ego car is our test subject. And this can take several forms. So the logic that controls the car can be directly running inside the simulator or outside it. When you run something outside the simulator, this can be an agent that it runs in the main process. So beside or along with the test case, for example, this is the approach adopted by Deep Janus, Deep Hyperion, the tool competition pipeline, or in a different process. So you can spawn another process or let another process connect to your running simulation and then let it download the data and drive the car. To define the test goal, we need to consider the fact that the problem that we want to solve and the test that we want to solve, either this be, keeping the lane, avoid obstacle, avoid pedestrians, recognize traffic signs. This is problem and application specific. So we need to find our own way to instruct our agent about what to do. And this can be done explicitly if you know how to do it, or sometimes it can be done also, let's say, implicitly. Other systems like DeepJanus, what they do is that they create tests for which the driving task naturally follow the setup. What I mean is, if you want to have a car that follow the lane, keep the lane, you can create one single road, place the car at the beginning of the road, and let it drive until the end of the road. So there is no need for trajectory planning, for telling the car where it has to go. It just follows the road. So let's see how we can use or exemplify these three different ways of including test subjects. The first one is to use the BeamNG driving AI. So BeamNG comes with a smart AI that can drive car. The API, the BeamNG Pi, exposes some methods to configure this driving agent. So here, what you can do is you take a vehicle, so you create a vehicle, you add it to your to your scenario, and then you say you can set up the mode of this AI. For example, manual assumes that you manually provide the destination or a list of checkpoints that the car should follow. Once you've done this, then the car will automatically drive. It's not that it's disabled. So in this snippet here, what I've done is I generated a road. I define a destination point as being the basically last point on the road, and then I added to the scenario a checkpoint. So a checkpoint is a specific point that has an ID that then can be used to instruct the BeamNG driving agent. Another way is a code, for example, an actual driving agent that will receive, for example, camera images and other data, and then will compute the control commands. And this is what DeepJanus and DeepHyperion tools, for example, do. The upside is that it's simple. You can basically, in the loop where you pull the data and then you pose the simulation, you can forward the data to the driving agent that computes the control. But it also requires installing all the driving agent dependencies within the other components. And this may or may not be feasible in solution. But assuming that it's possible, that's how it looks like. You can use a camera sensor, and the camera sensor in BeamNG provides you 4 different types of camera. The color one, which is what we are going to use, but you can also have pixel perfect annotation, depth cameras, and instance value that tells you exactly what's inside the image to help you testing different levels of smartness of your AI. So let's see how, for example, DeepJanus does it. So what it does, and the code that show here, it's a simplified version of what's on the website at this address, is it defines an NVIDIA predictor, which is a class that loads a Keras model that was pre-trained on images collected from BeamNG.Tech that predict a steering angle from an image. This is the classical setup of a end-to-end steering predictor. Okay, it gets an image from the simulator, it predicts a value of an angle. But because we need to drive the car, we need also to compute its speed. This component, given the steering angle and a limit on minimum and maximum speed, it computes also the throttle command. Once you have this model, once you have this component available, assuming that you already have a pre-trained model as I do, you can put it into the actual execution. And in the actual execution, what you're going to do is create your scenarios, defining the road and the initial placement of the car as we have done it before. You load your models that specify the weights of your network, and then inside a big while loop, you pull the data, you get the data, for example, data from the camera, and then you ask this model to make the prediction. And once you have this prediction, you can apply the control command. Once you have applied this, you can resume the execution of the simulation. We are still running into the synchronous mode. Then the control will be applied for the next control cycle, and then you come back after you collect new data, and then you repeat. The test creates a road. It's not a straight road, it's a curvy road. Then it starts TensorFlow, and then it shows you the camera images that are collected from this camera sensor. So the camera sensor collect the image, pass the image to the deep neural network that create the controls, send back to the network to the car, and then repeats the loop. The last possibility is to run everything into a separate process, and this is what, for example, the Asphalt tool does. And then the child process or the sub process, what it can do is it can query the scenario, the current scenario that is loaded in the simulator, and query the map and its position using sensors. And based on this and some other parameters, it can also plan the control. So that's how I can configure the test subject. The last piece for this part is adding some spice, adding some additional dynamism. Okay, for example, random traffic and controlling non-playing character cars. So here I'm not gonna show the traffic API. You can read about that on the website because I consider that to be an advanced feature, so will not necessarily fit this basic tutorial. So the way to control this NPC vehicle is either by using a checkpoint or by generating a trajectory, one of those scripts. So for the checkpoint is exactly what we have decided before. You tell the car, drive to this location with this maximum speed, and the car will drive itself. Okay, so you can use this to create, and make the other cars move on themselves. The other possibility, or a second possibility, is to generate this script where that creates a trajectory implicitly by specifying a sequence of nodes that must be reached in time. So here, for example, I exemplify this saying that at time 0, when the simulation starts, the car must be in the initial position in this leftmost node. Then after 1 second, it must reach this other node. After 2.5 seconds, the next node, and so forth. And because the nodes are displaced, the car will turn left and right. So this is how it looks like. So you have a trajectory that it's made of nodes. Nodes are basically dictionaries that contains X, Y, and Z that tells you where the car must be, and a T. T is the time since the beginning of the simulation in logical time, not in real time. And in this case, what I've done was to define an internode distance of 20 meters, and then have a loop that basically place one point, one of these nodes, every 20 meters on a straight line, and tell that the car must reach the nodes in 2.5 seconds. Then what we need is to create a vehicle, add the vehicle to the scenario, and then set up the vehicle AI with the set script. And this is how we can, those are all the pieces that we need to create tests. Tests can be created manually, of course, but then we can also use these pieces to create tests automatically. In this tutorial, I'm looking at the two main forms of test generations that I'm aware of when it comes to simulation-based testing, which are parameter exploration. We define one abstract scenario, and then we instantiate this by giving value to parameters and generate many concrete scenarios. The other form of automated test generation in this context is the one that rely on procedural content generation, where we can generate many abstract scenarios and either one or more concrete instantiation of those scenarios. So the first case, which you can find implemented into this automation example 1.py, is following a drunk driver. So the idea is that we start configuring the hidden car that the ego car should follow to follow a straight trajectory on a straight road, driving at constant speed. And then we start mutating this trajectory by changing the lateral displacement of these nodes that form a trajectory and the time between the nodes to create some sort of wiggling or let's say weird driving behavior, as you may expect from a drunk driver. So we can increase the speed, decrease the speed, keep the speed at the same time, and turn left and right. So let's see how it works. So this file is already available on GitHub under automation example 1.py. So because I'm expecting to run many tests, I'm gonna create one shared BeamNG simulation into the main file before invoking the main method. And then inside the main method, what we are gonna do is we create an initial individual. In this case, I'm not gonna create a random individual. I always create this straight line made of nodes that are equidistant, meaning that the car will travel more or less at a constant speed. Then I define a generic execute experiment that takes one of these individual, meaning this trajectory, create some debugging information to visualize them by creating some spheres. And then what I do, I place the ego vehicle at the beginning of the road. I place the heading vehicle 20 meters in front of it, and then I define a destination point. And then I define the aiding vehicle to follow this trajectory that we are creating, and the ego vehicle behind it to reach the goal waypoint at a given speed. In this case, the fitness function is going to be the distance between the two cars that must be minimized. To mutate the system, the trajectory, I have immutator operators that either move the point on the side or change the interarrival time, so we can control the speed of the aiding vehicle. So how does it look like for real? So we can run the script automation example 1. I'm not going to use unit test or PyTest. Everything now it's in a basic script. We are going to see that, and then once again, this simulation is sped up to avoid spending too much time looking at and loading screens. We generate the first individual, and then you see that the yellow car, which is in front of us, is simply going straight until it reaches the end, and then we start mutating it. Those are minor differences, but then sometimes we have better mutations for which not only we change the car that is now driving left and right, but we also drastically reduce its speed. So it passed from 28 km per hour to 16 at some point, and then you see that the ego car is getting closer and closer to it, and then this improved the fitness, and then at this point, bam, the car crashed into it. So we managed to find a way to crash this car by modifying the trajectory of the aiding vehicle. So if you want to find more, you find and discuss about this, you can follow us. You can check out these resources. We have the SBST workshop documentation from BeamNG, the tutorial, this tutorial here in bold, the pipeline competition, and many other tools out of there. So with this, I thank you once again. So my name is Alessio Gambi, and with Pascal Maul and Mark Mueller. Today we have presented to you this tutorial on simulation-based testing with BeamNG.Tech.